Okay, this is going to be part 3 on our harmonic oscillators. So this is section 2.3.1 about the algebraic method. So last time we stopped with a couple of important results. So we stopped with this result here, which is that when we made up these operators, a plus and a minus, we had the fact that they don't commute. So we have a factor here if we take the difference between a minus operator times a plus operator minus a plus times a minus, what we get is a factor of h bar omega. So if we plug those back into our Schrodinger equation, what we have is a minus times a plus minus 1/2 h bar omega, acting on our wave function psi equals the energy psi. And conversely, we have a plus a minus plus 1/2 h bar omega, acting on psi equals the energy times psi. So our Schrodinger equation is the Hamiltonian operator acting on psi equals the energy times psi. So for a simple harmonic oscillator, commonly abbreviated as SHO, our Hamiltonian, so this is our total energy of the whole system, is going to be either our ladder operator a minus times a plus minus 1/2 h bar omega, or we could have it this way. So two ways of looking at the Hamiltonian. Those are equivalent according to this equation up here. So two ways of doing the same thing. And we can choose how to approach it out of convenience. You will see in a moment why I called them a ladder operator. So this is fairly explicit for Griffiths. And Griffiths is a good textbook for showing a lot of work, but sometimes he does gloss over algebra, which can be a little bit confusing, especially if you're just doing this for fun and not for a class. That's where doing the problems really helps you out. So what we have here is that if psi satisfies the Schrodinger equation, this guy, so if psi is a solution, meaning we have something whereby the total energy operating on the wave function equals the energy of the wave function, then what we should have is something like, the whole point of going through all this exercise is to have something where this solution to the Schrodinger equation should produce the energy plus h bar omega. So it might seem like we've done a lot of work so far to get these results without really any, say, concrete motivation. This is now our concrete motivation. Our whole point was to get something that will raise the energy by a specific amount. So let's go ahead and see if that's true. So the claim is that if this is true for a simple harmonic oscillator where those Hamiltonians are valid, so where the Hamiltonian is going to be these operators plus or minus equaling plus or minus 1/2 h bar omega, then what we should see is the Hamiltonian acting on A plus psi equals E plus h bar omega A plus psi. That's our expectation. So this would be what you would call like our hypothesis. This is what we're going to test. So if this is true for harmonic oscillator, this should also be true. And let's go ahead and test that. So let's start, we could do it either way, but I'm going to do the positive values. So we're going to do A plus A minus plus 1/2 h bar omega acting on psi equals this. So this is our first statement. If this is true, if this, then what we expect is this. So now let's prove it. So first we're just going to look at the right-hand side of the, left-hand side of the solution the whole way down. So I'm going to go ahead and distribute this A plus operator. So I have A plus A minus A plus plus 1/2 h bar omega A plus acting on psi. Now A plus does not affect h bar or omega. H bar is a constant and omega doesn't depend on x. So remember A plus, might have forgotten because it's been a while, but you can always go back to the other videos. A plus is this guy. So 1 over the square root of 2 times the mass all times h over I times the derivative with respect to x plus I m omega x. So if I apply this operator on something with an x, the order does matter because then I have to take the derivative with respect to x of what I'm applying it to. But since it doesn't depend on omega or h bar, this derivative, it's not going to affect it. So I can move that A plus out in front. So operators you do have to be careful with. This is not always the case where the order doesn't matter. For multiplication of numbers, the order does not ever matter, but for operators it can matter. I said if there was an x here, we certainly could not do that, because if I were to move the operator to the left of an x, then I would have to perform this derivative operation on that x, and that is not what this equation says is appropriate to do. Since I do not have anything that depends on taking a derivative or an integral with respect to h bar, which is a constant, or to the frequency omega, I can move it out in front. And now that I've moved it out in front, I can conveniently just factor it out. And what you might notice here is now I have a minus times a plus. I'll go back here in my Griffiths book to take a look at that. I would like to take advantage of this other equation. But I have a minus times a plus 1/2 h bar omega. In order to exploit this equation 2.43, I need to get a minus h bar. Now fortunately, what I can do here is do like the world's most simple arithmetic, which is 1/2 h bar is the same as h bar minus 1/2 h bar. So if I have 1/2, that's the same as saying I have 1 minus 1/2. That's like our really, really stupid simple step that is going to take advantage of here. So I have a plus times a minus a plus, and now I'm going to say that's minus 1/2 h bar omega plus h bar omega times psi. Let's go ahead and just sort of distribute out that psi so I can get it in the same format. So I'm going to have a minus times a plus minus h bar 1/2 h bar omega all times psi plus h bar omega psi. I did that so I could have this format in here. So now I know that this guy all here equals E times psi, because that's what I spent an entire video proving before. So now we have A plus times E times psi plus H bar omega psi. Now again, I can switch the order here because my energy is a constant. So that means that my A plus operator, taking a spatial derivative on it, doesn't matter. It's not going to affect a constant. I don't have an x dependency of my energy, basically. My energy is a number, not a function. So I can rearrange this to say I have, oops, and then here, I forgot to distribute out my, actually we'll just put parentheses in. There we go. So let's go ahead and factor out the psi. And then I can factor out, I can push the A plus all the way through because it's not going to affect the order. So I have E plus H bar A plus times psi. And that equals the thing that we started with, which was our original Hamiltonian. A plus A minus plus 1/2 h bar omega times A plus psi. So there we go. We have shown, happily, that if I apply the A plus operator to a wave function that solves the simple harmonic oscillator Schrödinger, what I get is an energy increase of h bar. So what this means is that my energy with each ladder operator applied to it is increasing by h bar. So this is why it's called a ladder. So I could have, energy 1, energy 2, energy 3, and so on. And the space between each one of these energies is h bar omega. Omega being the angular frequency of the oscillation. So this energy landscape looks like a ladder. If I apply an A plus operator, I go up one ladder rung. If I apply an A minus operator, I go down one ladder rung. And we can do the same proof with the A minus operator. So in that case, we would just choose this guy for our Hamiltonian and have it act on A minus times psi. We do the exact same thing here, except you'll notice that to get negative h bar, negative 1/2 h bar, what we have is negative 1/2 is the same as negative 1 plus 1/2. So we will, instead of getting a positive h bar omega, we will get a negative h bar omega. So our energy will go down by h bar omega. So hopefully this is a pretty good argument for how useful this technique is, right? So this technique is very helpful because now we have found out what the spacing between each rung on the ladder is. And here's a nice picture of that. So this is what our energy looks like. If I apply a raising operator, I go from energy E to energy E plus h bar omega. If I apply the ladder operator twice, the raising ladder operator twice, I get energy plus 2h bar omega. Conversely, if I have some wave function that satisfies with energy E and I apply my lowering ladder operator, I get that energy minus h bar omega. Now here's a very important consideration for us, is that there is a bottom of the rung. Like there is a bottom to the ladder. So we do have to consider that. If we're looking at a simple harmonic oscillator potential, it basically looks like a parabola, which we went over in the first video. It has a bottom. So that means there is a lowest energy possible. So we have to take that into consideration for our solution. Like our energy, we can't just keep going down to negative, because a minimum does exist. We actually had this condition in our square well too. You know, if this is 0, we can't have energy be below 0. So I guess I should write it like that. Our energy couldn't be below 0, because that would be not inside our energy well. Same with the harmonic oscillator. We can't have the energy below 0 because we don't have a physical system that's allowing for that. It does have an energy. Now, we do have this, that we went over this, getting a state less than 0, according to the general theorem of problem 2.2, it doesn't exist. So there is a video on problem 2.2, if you're wondering. It is way, way back in the beginning, before we even got to square wells, which is saying that E, the energy, has to be bigger than the minimum value of the potential. If my potential has a minimum, like it does for a simple harmonic oscillator, like it does for an infinite square well, there is a distinct bottom of the well. The energy of my particle cannot be outside that bottom of the well. So a classical example of this is, pretty much you have a ball rolling down the hill, right? At this point, the potential energy, usually a U, is minimum. So at this point, the potential energy is a max. If we're talking about a ball rolling down the hill, the potential energy is the energy from gravity. I can't ever have that potential energy equal something that corresponds to a position down here. In other words, I can't roll a ball down the hill and expect it to go down under the hill. The ground is preventing it from going under. The ground in this case, in this classical case, is the boundaries of our potential. In the case of a simple harmonic oscillator, you can most certainly have, like you could take a ball and roll it down a hill, and it will oscillate back and forth. It'll go up and down and up and down. With no friction, it would do it forever. Same thing with a pendulum. The pendulum's going to swing, and it's going to swing back and forth from gravitational potential energy. If we were to map out its energy in either one of these cases, it would look like a parabola, just like the problem that we're solving for now. So the source of our energy doesn't need to be exotic for the math to be this complicated. This is still valid for any of those cases. If, like your typical quantum cases, usually you're dealing with things that are small, because quantum mechanics is a small correction to classical mechanics. So typically you're looking at particles, like maybe a proton or an electron. So it's not going to be normal for you to use gravity there. Certainly not at all. Gravity is a weak long-range force that we haven't really quite figured out how to get into small little cases like this. So while I can use the analogy of a ball rolling down the hill in your typical quantum system, what I'm usually going to be talking about for potential would be like, say, atoms connected by some bond strength. which will be determined by weak force, or you could call it electroweak force. So we'll be looking at physically cases like, atoms on a spring bouncing back and forth. If we were to map out the motion and the potential energy of that, it would be a parabola. This could be electric force or weak force. So we'll just call it electroweak force. Hopefully that convinces you why it's important to consider this part here. While this guy right here, while our ladder operators are very useful and they're very nice, like I think we've shown it's a really nice, easy way to calculate going up an energy level, down an energy level. However, we do need to justify that there is a bottom. So that means that since there is a bottom, we have some bottom rung wave function. We can call it, like our ground state, psi naught. So we have some psi naught where if I apply an A naught to it, or A minus to it, I get a 0. So that does have to exist, because this is physics, not math. Has to exist. So let's go ahead and work that out. So my A naught is 1 over square root 2m h bar over I d dx, acting on psi naught, plus I m omega x acting on psi naught, and that equals 0. Whoops, sorry, this was the lowering operator, so that is a negative sign. There we go. Just this guy right here. Now we're going to go ahead and solve that. This is like the one time that Griffiths is explicit in solving a differential equation, but we're going to go through it too because it's very handy. Okay, first of all, I can multiply both sides by square root of 2 times m, and that just goes away because anything times 0 is 0. And then I can add this to both sides. So I get h bar over I d psi dx equals negative I, sorry, that's positive now, I m omega x psi. Multiply both sides by I over h bar. So then I get negative 1, and I get m omega x over h bar psi naught. Okay, so here I have the change in psi naught divided by the change in x, or the slope of psi naught with respect to x, equals this. Since this is very straightforward, we're just gonna actually hash it out. For the people who don't do a lot of math, there will come a time where we can't actually solve things explicitly, especially a lot of these differential equations. And you typically, what you do is you guess, and then you test out your guess to see if your guess worked or not. This case is simple enough, and if you ever wondered why people like Leibniz notation over Newton notation for calculus, you're about to see why. I don't even think I could reproduce Newton notation at all. Okay, so what I'm going to do here is I have change in psi naught over change in x equals this whole stuff. So I am going to just multiply both sides by dx. So I have change in psi naught, d psi naught, equals, I'll just say negative dx times m omega x over h bar times psi naught. Now I want to actually do this operation. I want to undo this derivative operation. So what I'm going to do here is I'm actually going to separate out these variables, right? I believe we did separation of variables briefly before, but don't worry, we will get back to it. So basically what I have is all my psi naughts on one side, because I have the change in psi naught, and I'm comparing my change in psi naught to my change in x. And because Leibniz notation is very nice and handy, I was able to symbolically do that with the same algebra rules that I've always used. Now it's not exactly the same as algebra like you did in, I don't know when you do algebra, I have no idea. However old you are when you do algebra, I seriously don't know. 6th grade, 7th grade? It's not exactly the same as that, but the symbols that you follow using Leibniz notation are the same, so that makes it very natural to follow. What I want to do is I want to compare the changes in the psi naughts to the changes in the x's. And to do that, I just need to have all the psi naughts on one side and all the x's on the other side. Now I have basically my derivative of psi naught times 1 over psi naught equals the derivative of x times mass times angular frequency times position divided by h bar. Now I can just integrate both sides. So I'm just going to integrate both sides, because whatever I do to one side I can do to the other side. My integral of 1 over psi naught with respect to psi naught is just natural log of psi naught. I don't have limits here, so there is a constant. I'm just going to throw the constant onto one side because it's just a constant. I really don't care about it that much. Now, my other one, it does not depend on mass times omega over h bar. But then I have the the integral of x with respect to x, and that's going to be x squared over 2. And then we have some constant. I technically have a constant over here and a constant over here, but what's the point? Let's just put them both on one side. It's just a number. Okay, now we solve for this guy by taking the exponential of both. So the way to undo a natural log is to take the exponential of natural log, and that just equals psi naught. We take the exponential of both sides. What we end up getting there is we have e to the m omega x squared over 2h bar, and then we could say that's times e to the c, which is just a constant. So since we were using a before for normalization, we're just going to call it a again. And I'm going to call it a naught because we're talking about psi naught, right? So we have psi naught equals some normalization constant a naught, because this does have to be normalized, times this guy here, which you'll notice is a nice, Gaussian shape. Yay! So now we know what psi naught, although I specifically could actually write it as psi naught as a function of x, because clearly psi naught does depend on x. So we know the shape of our psi naught. That's happy. So this is the lowest possible wave function, or the wave function that corresponds to the lowest energy. So I guess what we really care about is what is E naught? What is our lowest energy? So we can go ahead and just plug this into the Schrodinger equation. So what we have is A plus A minus plus 1/2 h bar omega acting on psi naught is going to equal E naught times psi naught. And let's just go ahead and work that out. So I'm just going to multiply through psi naught. And now my whole condition, like the whole way that I was able to find psi naught, was by knowing that this is 0. So that means that goes away. So I just have 1/2 h bar omega psi naught equals E psi naught. Doesn't matter what psi naught is anymore. I could plug it in, but it's really just going to cancel out. And what I get is that my lowest energy state is 1/2 h bar omega. So that means this bottom rung of the ladder has this energy, h bar omega. And then we get our result. So this is a nice result here, which is using that relationship, we can solve for all possible psi's and for all possible energies, because we know what the bottom ladder rung is, and we know what the spacing is. So if I know the bottom rung is 1/2 h bar omega, then I know what the next rung up is, right? So if E naught equals 1/2 h bar omega, then applying A naught makes E1 E naught plus h bar omega, or it makes E1 1/2 h bar omega plus h bar omega, and it makes it 3/2 h bar omega, and so forth. Now same with our psi naught here. So we have psi naught, I guess I'll say explicitly of x, is A naught E to the m omega x squared over 2h bar. So A plus operating on psi naught is going to equal psi 1. So that would be A plus A naught. And that will be E to the m omega x squared over 2h bar. Or I could also write that as just, now this normalization constant will change. We could call it A1. I could put my A plus there, and then it's going to act on this guy. Each state has to be normalized. Each energy has to be normalized. So if I extrapolate that out to psi n, I do that n number of times, I get normalization an. I get A plus raised to the n power, however many ladder operators I do, times e to the all this guy. And do the same thing with en. That's just going to be I'm always going to take in number of ladder operators plus 1/2 times h bar. And there we go. That is our simple harmonic oscillator. It's a very useful solution because simple harmonic oscillators are everywhere. And anything, well, basically oscillation is everywhere. And in a certain range, it's appropriate to consider it a simple harmonic oscillator as long as we have sufficiently small oscillations. Okay. Now it doesn't give you, so one thing that, like, unlike the square well, we don't have at this point a specific normalization constant a in, but we will get there. Now you can always work this out for each one. So here's an example of him working out psi 1, which is easy enough. You just do psi a plus e to the m omega x squared over 2h bar. And then we can just write out what a plus is. So we got that I over h bar d dx plus I m omega x, all acting on this guy. So that's going to equal a1 over the square root of 2m. And then we have h bar omega d dx, of e to the negative m omega x squared over 2h bar plus I m omega x times all this guy. And then we can just take the derivative of that. So the derivative with respect to x is going to be the derivative of the inside. So that is 2x which cancels, so 2x m omega over 2h bar times, negative, and then times the derivative of the outside, which the derivative of e to the x is e to the x. Those twos cancel out. So what we get is a 1 over square root 2m h bar over I negative times m omega x over h bar. I guess those h bars are going to cancel too. Times e to the negative m omega x squared over 2h bar plus all of this stuff times the same thing, so I can factor out that exponential, which is nice, so I don't have to keep writing it all the time. So I get a1 over 2m. Gonna go ahead and cancel out that h bar. Gonna bring my 1 over I to the top, so 1 over I is the same as negative I, so I can get rid of that negative sign, and I just get I m omega x plus I m omega x. Isn't that like really convenient how that worked out? And then times this guy. So then we have all of this, Now, here I have a 2, because that's just going to equal 2im omega x. So then I get 2 over square root of 2. I know most of you don't need this, but just in case. So 2 over square root of 2 is going to be the same as 2 times 2 to the negative 1/2, and that just equals 2 to the 1/2, or square root of 2. Same thing with the m, so I have m over square root of m, it just equals square root of m on top. And then we have our I, we'll put I out here, and then I have omega x, and then this guy. I suppose I could clean it up a bit to look like his, where I'm just changing the order because now I don't have operators anymore, so I'm okay with that. So I could do I, A1, I don't know why I put omega first, but sure, 2m, and then we have x to this whole guy. Just a convenient way to lump all those constants together. And then if we want to normalize that, then of course we will do our normalization, where we're going to have, dx of this guy times its complex conjugate. So the absolute value squared. So we can find A1 that way. And we could find it for anyone using this method. As he points out here, I would not want to calculate psi to the 50, which is reasonable, but you could do it. It'd be annoying, but it's not impossible. So there we go. That's the end of harmonic oscillators. That one was a bit longer than the other two, but I had more time today. Next, we're going to be tackling a couple of simple harmonic oscillator problems. So there are 4 of them to be exact, where we're going to be normalizing, showing some things about the operators in general, how they're working out. And then we're going to tackle the analytic method. That's probably going to be even longer because, yeah, this method is a little rough. It's not as eloquent as the ladder operator method. It's brute force. So that's what we'll be doing next. So look forward to some oscillator problems.